different places. And, light diffracts, continues to diffract as it's traveling. So between these two planes, the amplitude and phase of the light has changed. So therefore, by measuring the amplitude of the light here, amplitude of the light there, in technicality or in principle, you can actually find out the phase. But it's not that easy. We'll talk about that later. Also, this one very often actually is applied to what is called imaged objects, imaged and mainly imaged phase objects. Okay, so at the image plane, right? Image plane is almost very similar to the object plane, right? I mean, it's just a replica of the object plane. So really, around the image plane, if you move by a little distance, left and right, okay, then you're not traveling too far, right? You're traveling distances of delta z. So as long as the light is coherent in that little region where you're moving, you're fine, right? Because, light has to be coherent in order for you to see the diffraction effects. But, the coherence should be there only in that little region. So therefore, you can do away with, powerful laser sources with hundreds of, centimeters of coherence length. You can move to, at least in principle, light with less amount of coherence. Okay. There are some other details. Care should be taken when using TIE for edge reconstruction because, higher spatial frequencies need to be reconstructed. But I'll talk about that later on. So this is kind of a summary of what is done in transport of intensity. Now, see here, yes, we talked about the fact advantages over quote unquote interferometric techniques because, of course, there is no reference beam. Can anyone say what is the disadvantage with this technique just by looking at this figure? So as I said, all you need to do, okay, I'm saying, I'm trying to promote transport of intensity. I'm like a salesperson. Hey, it's very good. You take your detector, just move it here and there, and, you have all the information. So what is the problem? What am I hiding from you? A salesperson never says, the minus points. So can you tell me what the minus point there is? Oh, who will buy? I'll make sure you buy it. Okay, I'll give it to you for free. But my question really is, what is the disadvantage? So you have, yeah, go ahead. Not reconstruction distance, but how much you have to move. Okay, but how much you have to move can be figured out. Okay, can be figured out. You can find an estimate. That's a good question. But other than that, let's suppose we have a handle. Okay, how much we need to move. You shouldn't move like 1 kilometer. No. I mean, small distances, how much I'll tell you a little bit later on. But assuming you know that, even then, what do you think could be a problem in this setup? Oh, well, object could be any object. I mean, here I'm trying to just do a hologram of the shadow, so to speak, of the object. But otherwise, it could be a phase object. That's where it's used more likely. Oh, yeah, yeah, yeah. You can do reflection now. That's not a problem. No, see, the main problem is when you go to the lab and try to set this up, first of all, you have to make sure this light is going exactly along that optical rays. That's number one. Even when the light is going along the optical rail and then you're moving your CCD, you put some stand and you're moving the CCD along the optical rail, even motor, whatever you want, manually. You have to make sure it's moving exactly along that Z axis because, you're getting some recording. Now you have to use, the difference, for instance, in the intensities, or do some operation with the intensities in order to find the phase. So if pixel by pixel, those intensity values are not matching up, then you have a problem, right? Even 1 pixel difference could be a problem. Yeah, I mean, the thing is then now you see it's getting into more and more complications. You don't exactly know how much to move. So we have done experiments, of course, When in need, you have to do something, but that's the problem. Okay, so alignment is an issue. But Professor Nishal's group has actually found a way out. If you can do things electronically, much better. Okay, electronically, if you can change this path length or path difference, is better. Okay, so one way they have done, I'll talk about it in the last slide over here, is to use like a liquid crystal device to change the optical path length by changing the voltage. Then you are not moving anything. Okay, there can be other issues, but at least you have solved that problem. Okay, so anything that you can do electronically is better. These mechanical movements, yeah, it's okay, but not the best. Okay, but in principle, yeah, it works. Okay, so what is the transport of intensity equation? Like I said, when Teague was deriving it and published his paper, I was also deriving it. I published our paper in 83. Teague's paper came out in 82. All starts from the Helmholtz equation because all there is the coupling between the amplitude and the phase of the light. So here is the Helmholtz equation. Helmholtz equation has, I'm taking very simple Helmholtz equation. This E sub P is the optical field phasor, right? I mean, that's what the E stands for in the Helmholtz equation. So you can write the E as the amplitude and phase. That's all I've done. This is the amplitude. Amplitude is written as the square root of the intensity, and the phase is written as phi. Only thing I did here, and this is something to just be careful about. See this phi, which I have written with tilde on the top, a tilde on the top. This phi includes the propagational phase and other phases. Because this is a phasor, right? There's a relationship between a phasor and the envelope. The envelope is, the part of the phasor. The phasor is the envelope times e to the minus jkz. Okay, because jkz is just the phase shift because of propagation from one plane to another. So sometimes you'll see me writing the phi tilde. Phi tilde is the phase of the phasor, but for the envelope, the phase I'll write as phi. That does not have the propagational phase. So that's the only difference. But otherwise, no other difference. Now, if you just put this into this equation, the usual trick is to find the derivatives, and then when you do that, after that you cancel the e to the minus j phi, and then you have a complex equation. The complex equation has real part and imaginary part. So the real part has to be 0, imaginary part has to be 0. So it's a usual. Are you familiar with that? How you do that? If you take this, put it here, you get a complex equation. Every term will have e to the minus j phi. They cancel out. Rest of the equation is a complex equation. Real part has to be 0. Imaginary part has to be 0 because the right-hand side is 0. So what does the real and imaginary parts give? Well, this is the real part, okay, and this is the imaginary part, right? I mean, I've just written it in a concise form, and that's the way it comes out, okay? So these are two equations actually that I derived, in 1983. These are the same analog of those equations, just written differently, except here also I have some nonlinear medium. Nonlinear medium has an extra term. So forget about nonlinearity. Otherwise, they are all the same. So these equations have some meaning. So I'll get to that in a second because it's kind of important to know what it is. So let's look at the first one, like this one, okay? So this one, what does it say? So it says that the dot product of the gradient, okay, of the phase equals k0 squared plus something else. All right, forget about this last term for now, okay? Forget about the last term for now. If you just look at this equation over here, okay, this equation is really like a simple equation that describes the propagation, as people call it, of rays. Why rays? Because, this gradient of phi, that's the phase front, right? Phi is like a phase front. Gradient of phi is perpendicular to the phase front. And that direction is the direction of the ray. So if you look at Born and Wolf's book, that is written as S, okay? Excellent. Oh, that's fine. At least that's good. The net is there.
Oh,
Yeah.
should take over.
All
All
right.
right.
No.
No, there's a feedback.
Okay. All right. Thank you. Can everyone hear me online as well? I hope so. Okay. Okay, so whenever you have the gradient of phi, so phi is like a phase front, right? Like a spherical phase front, say. Okay. So gradient is, normal to the surface. And normal to the surface defines the direction of the ray. Another word for ray is iconal. So in Born and Wolf's book, that is written as the iconal S. Okay. Typically in Born and Wolf, this guy divided by K0 is called the iconal. So here, this del phi gives the direction of the spatial rate of change of phi or the local direction of the rays. And in general, what do rays do? They travel in a straight line, remember the good old thing? So if you did not have this last term, this one, from here you can show that the rays travel in a straight line. That's pretty much it. So what's the essence of, what's the meaning of this term? Well, this term takes into account the effect of diffraction. Okay, because diffraction, remember, is called bending of rays. Okay, and the bending of rays happens because you have some, profile in the amplitude. That's why you have the bending of the ray, like a Gaussian beam, right? Gaussian beam spreads because it has, a profile in the amplitude. Are you okay with this? So this last term is in fact the contribution from diffraction. Okay, and you can see it in other ways as well. You can show that this equation will actually, in fact, give you, the diffraction equation that we have, and from here you can derive the Fresnel diffraction formula, and that's there in my book. I didn't notice at that time that all of this had to do with transport of intensity, but okay. In fact, this is not the transport of intensity equation. This is the transport of ray equation, if you wish to call it. Later on, okay, I have called it, and other people have called it too, transport of phase equation. Okay, because this shows how the phase is getting transported. Are you okay with this? So that's the essence of this first equation. So remember, the first equation has to do with how the phase changes, and it's also connected with diffraction. How about the second equation? This was the second equation, right? This second equation also has a lot of meaning. So what's the meaning from this equation? Okay, I've not written all the details, but there is this theorem, in like electromagnetics or even in calculus. It's called like the Gauss's theorem or divergence theorem. So, if you take this equation, right, and if you integrate this, okay, around a closed surface, then that becomes a volume integral. Remember, that's how you convert a surface integral to a volume integral. Got it? Okay. So then, if you did this, okay, when you converted it to a volume integral, or, if you took the integral and wrote all of that, you're going to find that this equation is really a restatement of the conservation of energy. Why? Because when you integrate all of that, what you're really finding out is the total flux, as they call it. These guys like to use the word flux, electromagnetic flux coming out of a volume. And the net flux coming out of a volume should be zero, because, if you have no sources inside, the total flux is zero. Make sense? So really, this equation is a restatement of the conservation of energy. This is something I realized way back there in the 82, 83. And these are very important things here. So these equations have a lot of meaning. But as it turns out, this, in fact, is the equation. This, in fact, is the equation from which you get the transport of intensity equation. Because why? From here, as you will see, this shows how the intensity is going to change plane to plane, which I'll show in the next slides. So this kind of approach, according to me, is better, at least to me, because it tells me exactly what these two equations are. Are you okay so far? So therefore, as you'll see, the transport of intensity equation is really a restatement of conservation of energy. That's it. And really, that's the principle behind it. When you go and measure the intensity, total intensity from one plane to the next plane, intensity is conserved. Which, in other words, also means it does not take into account the effect of diffraction, because diffraction is in the other equation. So if you want to be more exact with using the transport of intensity equation, you should also incorporate the transport of phase equation. In fact, that's what we have done. You can recursively solve, which is hard. Okay, so no need to do that. It works with only one most of the cases for small delta z. So that's why people just use the transport of intensity equation. But if you want to be more exact, you should use both the equations. Because you have, if you solve one equation, if you solve one equation with two unknowns, can anyone believe it? No, right? You need another equation to check. As simple as that. Yet, people just worry about this equation and keep on finding out lots and lots of different ways to solve this equation more accurately without looking at the other equation. I don't know why. All right, so you should always ask yourself these questions. That's another thing. There's lots and lots of papers, you'll see. All right, let's go next slide. Remember I said that this phasor is related to the envelope through this very simple equation. This is just a propagation term. So instead of starting from that Helmholtz equation, if you put this in the Helmholtz equation, you get the what's called paraxial wave equation. And paraxial wave equation you get when you make an assumption. The assumption is that this guy varies slowly with respect to z, the slowly varying approximation. Okay, I'm sure you have seen that, how to go from the Helmholtz equation to the paraxial wave equation. And solution of the paraxial wave equation, which we saw in the first lecture, this gives you the transfer function for propagation. So that's another way to solve that equation. But you could also solve it by, breaking it up into, amplitude and phase. So here, again, the amplitude is the same because these amplitudes are exactly the same because it's multiplied by e to the minus jkz. The phase now is to be written differently. I'm writing it as phi. So what's the difference between the phi tilde and the phi? The phi tilde is just phi plus k0z. K0z is just the propagation constant. Are you with me so far? So then if I take this and plug it in this equation, again, same thing like I did for Helmholtz, I'm going to get two equations separating out the real part and the imaginary part. So the real part is this first line, okay? Imaginary part is the second line. So the real part, which is the first line, has to correspond to this one, which I did before. And in fact, from here, you can also find that. Nothing difficult. And the second one, which is here, has to be the same as this one, right? So they are exactly the same. So which means the first one, once again, is the iconal equation in the presence of diffraction. And the second equation is, the conservation of energy equation. Are you okay with this? Guess what the second equation is called? Fancy, fancy word. Transport of intensity. That's exactly the transport of intensity equation. Okay? So are you okay where these come from? Again, these kind of things are not usually written in books or in papers. So you have to, all of this I had to find it out by myself. Best way to do these things is to sit down, spend time, don't copy other people's work. So, what is the first equation then? Just like the second equation has di dz or del I del z, right? First equation has del phi del z. So therefore, the first equation should be called what? Transport of phase. If I call the second equation transport of intensity, first equation will get mad. Or give me a name. So the name is transport of phase, right? So then when you are traveling, okay, when you are traveling from one plane to another plane, typically what you should do okay, really, is, you change the Z, right? You change the Z. Why you change the Z? To find out del I del Z. Okay, that's really how you do it, right? I mean, standard thing, derivative is, the value at one, Z minus the value at Z minus delta Z divided by delta Z, right? So, and there are fancy ways of doing it. Fancy way means, okay, you can take, forward and backward difference. You can have higher order derivatives. I mean, people have written paper after paper on that, okay, on how to estimate this del I del Z more accurately. Why? Because they want to find out this phase, right? They want to find out this phase. Of course, without ever looking at the other equation, which inverse square law actually is usually strictly valid for a point source. Okay, for a point source. If you had a point source radiator, yeah, then inverse square law is valid. But here, not really. Inverse square law is not valid. And why? Because there are several point sources and they're all superposed on top of each other because every point is radiating and giving out. And yeah, every point source radiating, giving out, they are decaying as a function of 1 over R, 1 over Z. But now you have to add all of those things. Are you okay up to this point? All right, let's move on here. So now, oh, another issue. There's a lot of issues here. So now I need to first of all, okay, this is called the TIE, transport of intensity equation. I need to solve this equation. So the question is how you solve that equation. Not easy. The first easiest case is a case where the intensity is a constant. Okay. So you might think, well, if the intensity is a constant, then what happens? I mean, when you move, is the intensity going to change? The answer is yes, it's going to change because of diffraction. Okay, if intensity is constant at one plane, it's not going to be constant at the other plane. Okay, and that's because, that intensity is really a result of, you know, imaging, for instance, in this case. But if you have an image of a complex field, when it moves a little, the amplitude and phase changes because of diffraction. All right? So typically, this equation, easiest way to use it is for an imaged object, and even better if the imaged object is a phase object, because for phase object, intensity is kind of constant, almost constant, right? It's never exactly constant in an experiment, but okay, approximately constant, right? Are you okay with that? So this was first applied, say, to intensity constant or imaged pure phase object. Why? Because if that is true, see, then here, this intensity guy can come outside that del operator, right? If intensity is a constant. That's a big help. Because if this intensity comes out, then you can take it to the other side and write it like this. Now, okay, you see, people are clever. They, kind of push in the fact that it's a function of x, y, and z. Uh, Not really true. Okay, approximately true. Okay, and it works. Okay, but most important thing is for image phase object, at least, at the image plane, this intensity will be a constant, and it should not be that much of a strong dependence on x and y. Okay, let's assume that's the case. Then how do you solve this equation? Well, so the best way to solve this equation, I mean, these are called the Poisson kind of equation. The way to solve this, best way and quickest way to solve it is by using the Fourier transform. Because, if you take the Fourier transform on the left side from property of Fourier transform, second derivative gives you like kx squared, k sub x squared, right? And k plus k sub y squared. Because every derivative pulls down a j times k sub x from the derivative property of the Fourier transform. And the right hand side, okay, so you have to measure this del I del z, z by moving, your detector at least twice. Some people move it 3 times, okay, fine. But you can find this one from measurement. After you have found this from measurement, you also take its Fourier transform as written over here. And then from this side, you have kx squared plus ky squared. So you divide by kx squared plus ky squared. and then you take the inverse transform, then you get the phase. Makes sense? So this is a very simple operation. Is everyone okay with this line here, how we did it? So you take the Fourier transform of both sides, and then this becomes kx squared plus ky squared times the transform of phi. Then that kx squared plus ky squared goes to the other side, as shown over here. And then this is all the solution you have in the spatial frequency domain. So you take the inverse transform and you recover the phase in the space domain. So that's it. That's the simplest way. And most of the time it works, actually, not that it doesn't work. So the other thing to realize is, this del I, del Z, sometimes usually people take the forward and backward difference, as you see here. Okay. Why? Can anyone say why people take this kind of formula for the derivative rather than, I of xy delta z minus I xy 0 over delta z? Yeah, it is. But my question is, why do people take this approximation for the derivative and not the first order approximation? This is mathematics question. Those guys who taught you calculus. The reason is because if you look at the order of accuracy, this is accurate up to second order. And that comes from the Taylor series expansion. Have you heard of Taylor series expansion? Okay. So if you expand, a function in terms of Taylor series in terms of about a certain point, then it involves the first derivative, second derivative, so on and so forth. So you can show that this is the better approximation. This is up to order epsilon squared, as they call it. So that's why people like to use this. Okay, that's not a big thing. And this intensity over here, this intensity, because you are measuring the intensities at plus delta z and minus delta z, might as well use those two. If you take the average of those two, then you will find the I at z, right? Or z equals 0. So that's how you solve this equation. Are you okay with how this is done? So that's the basic transport of intensity equation and its solution. And we'll see examples of that pretty soon. Now the question is, what happens if the intensity is not a constant, right? Because most of the time, you want to also use it for cases where intensity is not a constant. Now there comes a lot of problems. So what happens is, if intensity is not a constant, you cannot take this I outside, right? That's the problem. So then what do you do? Well, these guys, the guy's name is Nugent, okay? There are two guys, Paganini and Nugent. They worked a lot on this, okay? So they devised a way of how you could tackle the problem of non-constant amplitude object. Amplitude and phase, of course. So what did they propose? They proposed, oh, okay, since if I have something like this here, right? This is a function. This is a function of, space, R and Z. Why don't I define a new function which they called mu, as you see here. Okay, the new function is mu, such that the gradient of mu equals this whole thing. Now, who would think of such a thing? Well, there is a reason. Well, if you could think of a function, whatever the function is, fictitious for now, such that this guy can be written as the gradient of mu, see what's going to happen. Then here you can write the gradient of mu. If you write gradient of mu, that gradient dotted with this gradient will become the Laplacian, right? Then it will become pretty much like this guy, right? Similar to this, except I don't have phi, but I have mu. Are you okay with that? So then I can solve that equation, right? Then I can solve that equation. And then once I have solved that equation, then hopefully I can come back and solve this one, right? I can hopefully come back and solve this one. Again, all using Fourier transforms. So if you solve for mu, how can you solve for this one? Once again, what you have to do is again take, another Fourier transform on both sides, and then you can solve this one. I've left out that step, but if you solve the first equation by putting this in there, then find the solution of mu, and then solve this one. And how do you solve this one? As I said, by taking the gradient operator and dotting it on both sides. Then finally you can find the phi. And that solution of phi is written over here. It's kind of long. Okay, why is it long? Because, see here, first thing you do is you have written this one as mu. You have written this one as mu. So the solution of this can be found by taking the second derivative and then the Fourier transform the second derivative. That's going to give you this term, this del perpendicular minus 2. That's how it's written, of this side. And then once you have solved that, then use this definition for mu, because see here, if you want to find this guy is 1 over I times this. That's what's written over here. And then you dot it with this del operator and then take the del of minus 2, del perpendicular minus 2. Then you have solved this entire equation. Now I have not written the solution or step-by-step procedure to get to here, but there are two missing steps. But I can tell you that this is the final answer. Are you okay here up to this point?
So you will implementing the minus sign the minus k.
Yeah, this k is just the propagation constant. Right.
Minus sign.
Minus sign was there before too. See, here was minus sign. Minus sign is always there. Here is minus sign. Minus sign is just from the algebra. Just from the algebra. So are you okay so far? So this is kind of the more general solution of the TIE equation when you have a non-constant intensity. And then this one is now, so all of these guys, see, like a term like this can be always solved in this fashion, in the Fourier domain. Because you remember, anytime you have this del minus 2 or del perpendicular minus 2, it's like dividing by kx squared plus ky squared. Does everyone understand that? The reason for that is, if you looked at this equation here, right? This one solution can be written as phi equals del minus 2, that kind of strange operator, del minus 2 of this. So how do you do that? Well, starting from here, you take the derivative and the Fourier transform the derivative, you have kx squared plus ky squared. Then you take it to the other side, it divides by kx squared plus ky squared. So the essence of that del minus 2 operator, so to speak, is in the Fourier domain to divide by kx squared plus ky squared. So that's why this one has been written here. Okay, these guys, had a step-by-step procedure to do that in terms of a flowchart. And this flowchart is actually very important because this flowchart, in fact, they wrote it and then they applied for a US patent, and they have a patent on this, on the flowchart. Yes, on the flowchart. You cannot have patent on a computer program, but you can have patent on a way to solve a problem. Right? And this is used all the time. I'll come back to that in a second. But let me spend a little time, again, so this is around in the literature. I have issues anytime I'm trying to, understand something. So here is the problem. And, actually, Dr. Nischal also has in one of his papers in the Asian Journal of Physics, which is a local journal in India, he has also written about it. And because you cannot avoid it, it's there. It's a problem. What's the problem? Okay. So I have defined, a new function, mu. I have defined a new function, mu, such that the gradient of mu equals, some quantity I times, you see, the gradient of another scalar. Question is that valid? And I say no. And everyone says no. Why is that so? Well, very easy to show. You take this is a standard calculus problem. You can take this guy and you can take, this is a formula, it's a vector identity. You can use the vector identity. So what you do is you take the curl of this guy, because this is actually a term like this phi times f. This is the vector identity. And then what you're going to see is that this assumption of this guy being defined to be the gradient of a scalar is only valid, guess when? When the intensity is a constant. So you're back to the previous case. If intensity was a constant, you don't have to go through all this trouble. But as it turns out, okay, it works even if the intensity is not a constant. So that's why people still use it. But it can fail, okay? If the intensity is wildly varying, this is not going to work because you are violating one of the basic vector theorems. Again, this is nowhere written. Again, the guy is trying to sell his product. Will he say that? No. So you have to find it. So I pointed it out in one of my papers, and I saw that Dr. Nischal also pointed it out in one of his papers, and I think everyone should point it out because it is true. Okay, so here, okay, so the way you actually solve that is a nice chart. I'm not going to probably find time to go over it, but typically what you do again, step by step, you see here, so this guy, del I del z, you start with that, and of course there is a minus k, okay, that minus k term is there. Then you have to take its Fourier transform, right? You have to take its Fourier transform. After you take the Fourier transform, you have converted this to the spatial frequency domain. Then what you have to do, well, you have to do this operation over here, right? You have to do this operation, and not only that operation, but on top of that, you have to do the other operation of the del, okay? So remember the del minus 2 was like 1 over kx squared plus ky squared, right? And del operator means differential operator. That'll be like j times kx or j times ky, right? So if you combine these two together in the spatial frequency domain, it's like j times kx divided by kx squared plus ky squared plus j times ky divided by kx squared plus ky squared. So that kx over ky squared or kx squared plus ky squared, he defines as this operator, f sub x. See, f sub x is kx over kx squared plus ky squared. So you take the Fourier transform, do that. Okay, so you're tackling the x part of it. Then you take the inverse transform. Then you divide by I as written over here. Then once again, you take the Fourier transform. Then again, you use that f sub x operator to take care of these two guys over here. And then take the inverse transform. So you have done one part of it, which is depends on kx divided by kx squared plus ky squared. Do the same thing for ky. Then add the two together, and then you have the phi. Are you okay? And this works, by the way. This works. This is a, anytime you have to use this transport of intensity equation for approximately constant intensities or slowly varying intensity, this works. Yeah, correct. He's a mathematician, but guess what? Mathematician hid something. This is never written in his patent. He's a clever mathematician. Okay, so now that you have found the phase, okay, remember I said the phase is found typically at the image plane. Then if you have found the phase at the image plane, that's it, because image plane is the same as the object plane, right? But in general, if you are doing it in general for arbitrary distance of propagation, then of course you have found the phase where you have made these measurements for the intensity. So then you have the intensity and the phase here, but if you want to find the intensity and phase of the original object, you have to do the back propagation, right? That's as simple as that. You have to do the back propagation. That's it. So are you okay with the transport of intensity? Okay, so the first experiment on transport of intensity, this was done actually at MIT, and MIT did this experiment with a phase object, all right? What phase object did MIT choose? A piece of diamond. Yeah, this is a piece of diamond. Uh, in my lab, I took phase object as a water drop because diamonds are expensive. MIT can afford it. I cannot say. Okay. So anyway, so they used diamond, okay, right here. It's not very polished, okay, so it was not that expensive, okay. So that's what they took as the phase object, and then they found the phase profile, the imaged phase profile, and it worked out very well, as you can see. So this was a good demonstration of the first experiment where, this object was actually done. Then guess what? They also did this transport of intensity from different directions, just like tomography. Okay, And then they did some multiplicative technique, and then they found really a true 3D shape of the diamond. All right. So next time you go to buy a diamond, take your transport of intensity equipment with you. Guys, take care. All right. As I said, transport of intensity is only one part of solving the Helmholtz equation. So what we tried actually is to use both transport of intensity and transport of phase. Okay. Because one provides a check on the other. So this work actually came out, or we published it in about 2016. So again, same kind of thing. So here is our phase object. Okay. So what did we do for the phase object? We took a bottle, clearly a cuvette, filled it with alcohol, added some red dye, and shined intense, focused green light. The green light will be absorbed. And what happens when absorption happens? Heat, right? So it heats up the liquid. When the liquid is heated up, it creates a refractive index profile, right? Because, the density changes. When the density changes, refractive index changes. So you create what is called an induced lens, really. But it's an induced negative lens. Okay, so be it. Doesn't matter. Why induced negative lens? Because where the heat is the most, okay, the density is the least, so the refractive index is the least. Okay, but anyway, it's a phase object. That's our phase object, as opposed to MIT's diamond. Okay. I mean, this one is used for focusing. Intense laser beam is used for focusing. And then we used a helium neon laser to monitor that phase object. Okay, so this lens is used really to focus the light, the green light, into this material and create the phase object. And then we probe it using a Heaney laser. Yeah. And that Kerr effect is right here. Okay, that Kerr effect, yes. That's why you see for this green light, you see all these rings in the far field. These rings are really a result of self-phase modulation. So this is actually another good thing because for those of you who know maybe a little bit of nonlinear optics, by counting the number of rings, you can say how much is the peak phase change. So if you have like 10 rings, 10 rings means inside the material, you have a peak phase change of 10 times 2 pi radians. So that also gave us a calibration of what is the peak phase change, because we are doing transport of intensity here first time. We don't know what the heck, how much phase there is, but that gave us a good way of, measuring or keeping track of how much the phase is. So what we did is we probed this, say, in the plane, going perpendicular to the plane of the screen with a Heaney laser, imaged it, and then we applied transport of intensity. But this is what we did. We didn't only take the intensity readings at two planes, we took in several planes. Why? I'll tell you. Okay. Look at the first equation. This is the transport of intensity equation. The next equation, which is from the diffraction, is the transport of phase equation. So what did we do? First, we took, as an example, say we took these two differences, say I1 minus I minus 1. Okay, then we found out the phase. So we found out the phase where? We found out the phase here in the middle between where these two intensities were recorded. Okay, so we found the phase there. Then, say for instance, we did this. We did I0 and I minus 2, took the difference, and then we found the phase. Then where did we find the phase? We found the phase here, right? And so on. Why are we doing that? If we know the phase at different planes, then I can go back to this equation, because this equation has del phi del z. Okay, then I know what that is. And then I can recalculate the value for the intensity. And then once I recalculate the value of the intensity, I keep doing that till I, converge. So like here. So first I started with measuring 7 amplitudes. From there I got 5 phases. From there I came down to 3 intensities. And finally I came down to 1 phase. Now you can keep on doing more and more, but this was just to show the point. And yeah, in fact, it works. We found a good estimate for the phase over here. The phase that we saw here was about, approximately like 30 or 31 radians, approximately that. And that's equal to, guess what? Kind of like 10 pi. Okay, so that corresponded with the number of rains. So it agreed. Only problem is, okay, this takes a long time, right? So if you can do with one with reasonable accuracy, that's fine. Yeah. This nonlinear sample responds to a focused green laser, right? Because the green laser, all the green laser is doing, it's making the light being absorbed in this red medium. And when it's absorbed in the red medium, then its temperature changes. Okay, so how you find out the refractive index profile? Well, you take the heat equation in steady state. So, I mean, okay, if you keep on heating the thing up, it'll start to have convection currents and so on. But kind of in steady state, if you take the heat equation in steady state and solve it with the source term, where the source term is like the intensity profile of this green beam, then you have the temperature profile. And of course, you also need to know what's called the dN/dt of this material. dN/dt means how much change of refractive index is with temperature, which is there in tables, like for alcohol, for water is there. So you can find that out. I used a continuous wave laser. Yeah. It's just a standard, argon laser. This kind of setup, why I did this setup, I'll tell you. Because this kind of setup is also something I set up when I was doing the first time the Z scan. Okay, so when I did the Z scan way back, first time in 1991, okay, that was like a couple of years after the guys in Central Florida did that experiment, Van Stryland. So that time, my PhD advisor, Corporal, he told me, hey, let's do Z scan. So he said, just buy some tea, green tea, okay, and make a green tea solution and then put red light in it. It'll absorb, and that works. Okay, so those days, green tea was not that popular in the United States. So what did I do? I went to a vitamin store. In vitamin stores, they sell tablets, tablets of like spinach. There are people who don't like to eat greens, right? So what they do, they take a tablet, which is one of the worst things to do. Okay, but what's that?
Tablets of spinach.
Yes, like a capsule. Inside is spinach powder. Yes, I took my spinach today. Yes, so that I took those, I bought those, and that had plenty of green that dissolved in alcohol, and then you could make that experiment. So later on, I bought some red dye to put in the alcohol, and then I used green light. Yeah. So, I'm sorry?
Vice versa.
Vice versa, right, exactly. Oh, just to absorb the light. Yeah, just to absorb the light. That's it. No diamonds for me. Okay, getting on. Another way, actually, to rather intelligently use the TIE, and this is what I think it is best used, is it can be used as a phase unwrapping device. It can be used as a phase unwrapping device. Why? Because you see, in this equation, when you're solving this equation here, even the simple form, when you're solving like this equation, right? This equation, you are not taking any tangent inverse operation on the computer. Are you okay with this? Whenever you're doing this operation, you're taking Fourier transform and then dividing by something, taking inverse Fourier transform. There is no inverse tangent operation. Great thing, because that means whatever phase I get is unwrapped, right? So I use it as a phase unwrapper, and it works excellent. So the first time we tried using it was, we said, okay, if you have a hologram, remember in a hologram, okay, you reconstruct the hologram. So when you reconstruct the hologram, there is amplitude and phase, and there's always this issue of phase unwrapping. So why not do this? Okay, you are doing everything numerically, right? So when you are back propagating, so let's suppose you have made the hologram. This is just the construction of the hologram. So when you are back propagating or forward propagating, wherever, to the image plane to reconstruct the hologram, anyways, you are doing it numerically. So why not find, the intensities at three different planes and then use transport of intensity, right? Very simple. And I get my unwrapped phase. Does that make sense? So I don't need to rely on this Puma, on limitations of Puma or whoever it is. I mean, I don't care. I use my transport of intensity from now on. So here, as you see, that's what we did. In this case, this was a test, first of all. In the test, what we did, we generated a hologram. That's why we call it a computer-generated hologram, okay? Because we generated the hologram on a computer, all right? Great name. So we used a Gaussian phase. Okay, that means the intensity was constant, but the phase looked like a Gaussian function. And a Gaussian function with a certain height, okay, like 10 radians, 20 radians, 30 radians, whatever, okay? And then we propagated that, and with a reference, then we made the computer-generated hologram. After we did the computer-generated hologram, then we did exactly the same thing as before. This was done, off-axis, then you again, take its Fourier transform, you crop it, usual stuff, and then you reconstruct it. When you reconstruct it, typically around the image plane, okay, you see around the perfect image plane, as you see, the intensity is, of course, uniform, should be. This is all numerically done anyways. But intensities at defocused planes are non-trivial, as you see. So all you do is apply the transport of intensity here in this formula, and then find the phase. Okay, and the phase is exactly correct, of course, as we started out with. Okay, so it worked in theory. Let's see if it works in experiment. So in experiment, so we set same kind of stuff up. Okay, so here we are actually doing exactly the same thing. We'll be recording the hologram, and then we're reconstructing it. That's all. Now, one of the things that we actually tried to do, because we are trying to, kind of show how good or bad this is without hiding anything. So we did this comparison between hologram recorded at wavelength lambda 1, hologram at lambda 2 wavelength. Then we also use what is called like the dual wavelength technique, because that also is a way of reducing errors because of phase unwrapping. And we also compared it with, the holographic reconstruction with transport of intensity. So all of those were compared together. So that's why you see here, okay, we did single wavelength digital holography, we did double wavelength digital holography, we did DH with TIE just to see which one is working better. Are you okay here? All right, so what did we use as a phase object? Well, we used different lenses. Okay, lenses are phase objects. So we found a whole bunch of plano-convex lenses in the lab. They are easy, right? So because one surface is plane, the other surface is curved. And, you can exactly find out, what's the radius of curvature of that surface. Okay, we used actually a profilometer. Otherwise, we also saw the focal length. They all agree. So there are different lenses with different radii of curvature. This particular one had a radius of curvature of like 500 millimeters, something like that. And then we knew the refractive index of the material. So we exactly know what the phase object is. And then, okay, so what we did is, we did, the reconstruction using single wavelength, reconstruction using double wavelength, and then reconstruction using one wavelength along with TIE. And these are kind of like the results over here. So this is for single wavelength recovery, double wavelength recovery, meaning, double wavelength means, the beat wavelength. And this is DH with TIE. Now, which one is better? Okay, I don't know. So how do I need to find out? Well, you draw a cross section and then see how those things look like. So these are typical cross-sectional results. So as you can see, this guy, single wave. So the one which is in black, the one which is in black, which you cannot see, is right here. Okay, this line right here. And why you cannot see it is because there is another line on top of it, which is the red line. The red line, guess what? This red line is DH with TIE. It matches exactly, as you can see, right? The one with single wavelength DH is a little bit higher, and the one with double wavelength is somewhere in between. Now, double wavelength has a disadvantage in some sense. Okay, unwrapping is better, of course, but the result is more grainy, as you can see. And the result is more grainy because I didn't go through the derivations. There is usually more noise because of the fact that you have a larger synthetic wavelength. So are you okay with this comparison? Uh, it works up to a certain point. These are lenses with other different radii of curvatures and other even different radii of curvatures. And what we found is, yeah, it works up to a certain point. As the radius of curvature of the lens becomes smaller and smaller, you start to see a little more departure for all of them, for all of them. But the departure for the DH plus TIE is the least. Okay, so DH plus TIE is still the best. Like here, see this guy over here? So this was the first case. It was exactly on top of each other. This one, okay, this is the actual lens shape over here. DH plus TIE gives this. Two wavelength digital holography gives this. Single wavelength gives this. Right? So clearly, DH plus TIE is a great way, okay, of unwrapping space. Again, I'm kind of exposing you to stuff that is very recent. Okay, I mean, all of this was just published, 2 years ago or something. Last thing I wanted to say is, remember I said the recursive way of doing this TIE plus TPE, recursive way takes a long time, yes, true. If you're only doing, TIE, no digital holography plus TIE. But there's a way out, kind of like I would say, like a poor man's way, if you wish to call it, which is to combine the TPE with the TIE in one step instead of two steps. So that's some work that I did with my student. It just published in 2021. What you do is, okay, this is the regular TIE equation solution, kind of the simple one. Here, see, there is a propagation constant K0, right? There's a propagation constant K0. Now, remember what we said, what is the essence of the TPE? The TPE comes from the iconal equation in the presence of diffraction. So what does diffraction do? Diffraction bends the light, right? Bends the light. Bending of the light can happen if you have an inhomogeneous refractive index, like in a fiber, right? There the light bends, as you know. So we thought, well, why not change this K0 to K0 times N, where N is a correction factor of a refractive index. That refractive index is kind of like a virtual refractive index, and it's coming about just because there's the shape of the light. That's why the light rays are bending. So we derived that actually, that N you can find out using the transport of phase equation. This is what the approximation is to N. And then, as it turns out, if you do apply it there, okay, then you can get the phase non-recursively, just two steps. And it works reasonably well. Not exact, nothing is exact. Okay, are you okay with this? I'll give you all these notes. Last thing, as I said, this is something, oh, look at the timing. I mean, he was waiting outside. So his group did, right? So I have to mention this because this is the electronic way of, changing that delta Z. So, in his case, this work, the first time, I think, is that correct? This was actually in 2019 and then he followed up with the paper, I guess. So this was done by one of your, is it former students, Alok
Yes.
Gupta? Okay. And how about Ariba? She's also.
Yeah, Riva is currently pursuing postdoc at University of Glasgow in UK.
Okay, okay.
So she is here. Probably she will come tomorrow.
Oh, nice. Okay, okay. So they worked on using a liquid crystal, okay, which you can change the birefringence and thereby also change the path length. I don't want to get into all the details. You can work out the details. The main detail here is, and this is in a simplified form, this equation. Remember, the transport of intensity equation was written before as del I del Z. Now it has changed to del I del N, right? by, again, they started from the paraxial wave equation, but instead, of having just K0, they modified it to n times K0, and the n came in from the refractive index birefringence of the liquid crystal, which is voltage dependent. So here you can put your liquid crystal there, change the voltage, and it's much more convenient, right? Because in this case, you take two intensities and then you subtract that and you can find out the phase, right? Again, I can send you also the abstract of that paper and the whole paper, follow-up paper as well. So that's, again, I will say a very good work in the area of transport of intensity.
Thanks, sir, because not knowing anything about transport of intensity, I learned from him.
Then he asks for my thumb, or I'll ask him for his thumb. No.
So I think, can we break?
Yes, I think I'm done. Actually, that's the end. You came in exactly at the right time. So thank you very much.
Comfort tea and then.
Yeah, thank you. And then I think Dr. Nisra is going to talk about some of his applications. Are you okay with this transport of intensity? All right, let's transport to T.
So in transport of intensity equation, so we got intensity at different jet velocity.
Right.
So this can